There we go. We're going to start by looking at cosecant today. Cosecant is the reciprocal of which piece? Sine. So this is very much related to the graph of sine of x. So what we're going to do is we're going to start by graphing sine. So we're going to get to practice all of our regular guys too. So since we're looking at our parent function for sine of x, we are going to number our x-axis the exact same way we did when we did the parent function for sine, where I do 4 units to a sine. You do not have to do that. I just find that to be an easy one to work with. So I'm going to number this off the same way, where we start with our pi over 4, our pi over 2, our 3 pi over 4, and our pi. But I don't want to have to number all of them because that's a lot. 1, 2, 3, 4. We got 2 pi. 1, 2, 3, 4. Minus pi. 1, 2, 3, 4. Minus 2 pi. So just numbering my x-axis out here. We okay? We good?
Yeah, we good?
Is it getting heated in the second row? I got more glue sticks if we need that. We're fighting over glue sticks. I have more. I don't know what's happening. I know none details. Y'all are getting heated. Okay. So sine starts where? What's our first point on sine? 0. Because if we think through our unit circle, that's what we're doing. So angle 0, we're right at 0. At pi over 2, what's our sine? It's at 0, 1, so our sine is 1. At pi, what's our sine? 0. At 3 pi over 2, what's our sine? -1. And at 2 pi, 0. That's our sine curve, like our first guy. From there, it just repeats. Continuing the pattern outwards, over and over and over, forever and ever and ever, out into infinity, right? I'm gonna give you guys I highly recommend drawing your sine on there. So put a sine on your graph. All right. So we know cosecant is related to sine, right? Because cosecant is 1 over sine, right? So I need to take the reciprocals of each of these values. What do we have problems dividing by? Like, where do we get asymptotes if we divide by what? 0. So every place that we have a 0, we're going to have an asymptote for cosecant because we cannot divide by 0. So we are going to have a gabillion and a half asymptotes. So every place that we have a 0 for sine, we're going to put an asymptote. And yes, you have to draw them. I'm going to do mine in a yellow. Whoa, way too chunky. So off of sine, still too chunky. Every place that we have a 0 on sine, we're going to put an asymptote for cosecant. So we're going to have one at 0. We're going to have one at pi. We're going to have one at 2 pi. We're going to have one at minus pi. Because we're going to take the reciprocal to get cosecant. But if I divide by 0, we get undefined, right? If it's undefined, I can't have a point there. It's going to turn into an asymptote. So I'll just write down. So our asymptotes are going to come from when sine of x equals 0. Which I'm going to show you how to like write what we actually want here in a second. So we have a lot of things that are going on with sine, right? Lots of weirdness. I'm going to just look in this space here, starting with this guy. I know we have a point at 1, right? We like that. What is the reciprocal of 1?
1.
1. We like that. That's nice. So our first point for cosecant is going to be right there. The points in here, are they less than 1 or greater than 1? Less than 1. If I take the reciprocal of a number less than 1, so let's say 1/2. What is the reciprocal of 1/2? 2. So it's going to be up here, right? So we're going to have a point up here. If I have a reciprocal of 1/2 on this side, it's going to go up this way. As it gets closer and closer to 0, it's going to get bigger and bigger and bigger and bigger. It's going to get bigger and bigger and bigger and bigger.
Do we only need those 3 points, or do we need like
You actually only need the center one. You do not have to find the 1/2 or the reciprocal. I was just doing that so we could visualize and see what's happening there. Okay, so all we need is the ones. Because if I have -1 down here, and I take the reciprocal of -1, what do we get? -1. If I take the reciprocal of something like -1/2, what are we going to get? -2. It's going to go down. More and more and more and more and more. Like this. Okay. As the pattern repeats, it's going to repeat. So we're going to have our points at the 1 and the -1 just like the others. And they're going to approach the asymptotes and not cross them. Yes. I agree. They are unpleasant and ugly. So technically the graph of cosecant is just that part of it. I find it helpful to include that part because it's easier to see. You do not have to include sine. I will not take points off if you do include sine. I tend to include it. If you just graph it like this, more power to you. I cannot do that in my head. That's totally fine. Which part? I mean, you can usually figure it out. You'll need to know sine and cosine, and you can kind of work it through the way we just did. But we are going to need to graph them. All right, so when we're looking at the pieces that we like to label, so our asymptotes, the period, all those kinds of things, we're kind of basing those off of the sine in a very similar way. So our asymptotes, the way we're going to write them is we're going to talk about how often they occur. So they're going to happen every time sine is 0. So in this case, it's at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 12 pi, 27 pi, any pi. So the way we're going to say it is our asymptotes happen whenever we have pi times some number, any number. The period is based off of the parent function, so just like we did for sine. So in this case, since our period's going to be that 2n. What's up?
For the asymptote, what if the number is on the fraction?
I'll show you. We'll get there. We'll get there. Our amplitude is going to be based off the amplitude of sine. It's going to be how far this point is from our center line. So in this case, it's still going to be 1. This was our parent function, so we didn't actually calculate our left or right endpoints. because we're not graphing sine, we're graphing cosecant, the reciprocal. What's up? We took the reciprocal of the gray line. So that was where I had my reciprocal of 1 is 1. So that's this guy. And if I look down here and it's a fraction, like let's say it's 1/2. If I took the reciprocal of 1/2, it's going to flip. It's going to be a 2, right? So it's up here. So the point I really want for my cosecant is up here at 2. Up here at 2. So as these get closer and closer to 0, they're going to get bigger and bigger and bigger and bigger. Bigger and bigger and bigger and bigger and bigger. In both secant and cosecant. Because in fact, secant is the exact same process as what we're doing with cosecant. Just based off of cosine instead of off of sine. The exact same process. Okay, so when we're talking domain and range, it's a little bit different. Because domain is really where our asymptotes come into play. Because they're important for graphing, but they're really important when we're talking domain. So thinking about our cosecant, I'm erasing sine for a second. What is our domain for cosecant? Yeah, it's everything except for where our asymptotes are, right? So it's all real numbers except for those asymptotes. We're gonna write it in shorthand. So I'm gonna put my sign back here for a second because I don't want to lose it. So our domain is gonna be all real numbers. I'm gonna use the capital R, except x does not equal pi n. It doesn't equal where our asymptotes are. I'm gonna erase it again just so we can look at it for our range. What is our range gonna be for cosecant? Was it?
Okay, negative infinity,
Mm-hmm.
negative 1,
Mm-hmm.
and then positive 1 to infinity.
Yes. I'm putting that back in. So we're looking for just the blue pieces for our range. It goes from, well, that's not a pen. Negative infinity to negative 1. And we include negative 1 because we had that point. That reciprocal at negative 1 was negative 1. Joined with 1 to infinity. So we include the union there. And we're going to practice this a bunch. To be fair, it is a college course. It is advanced. Though regular Precal's doing this today too. Because my neighbor came in and was like, oh, we're doing that today too. They're graphing cosecant and regular Precal. Okay. When we have cosecants that have transformations and things, we're going to apply the transformations to the sine and do the exact same thing. Okay, so we're going to change our parent of sine, which will affect how these ones go. Okay, we're going to look at them. It's the benefit of doing things like secant and cosecant is it lets us practice our sines and our sine transformations again. So we're going to keep working with these. Ready to see it?
Sure.
Don't throw your pen. No, you're fine. You're fine. You're fine. Because what we're going to do is we're going to graph sine with these same transformations. Think about graphing. Let me put it in gray just because it's not the one we want, but it's a relative. If we graph 2 sine of our 1/3 x minus pi, that's going to be our kind of base that we're working with. That's going to be the gray that we put it over. Because cosecant is based off of sine. Yes, but it's easier to graph the reciprocal off of sine than to do it independently of itself. Otherwise, you have to figure out where every one of those asymptotes and every one of those u's goes. Ew. Graphing it off of sine is the easiest way that I know of. In fact, it's the only way I know of. I wouldn't know how to do it without graphing sine. Okay. All right, so we're going to start by basing everything off of sine. So, what is our amplitude? 2. It's that number in front. Still the amplitude for cosecant. How do we find the period? 2 pi over 1/3. We take it over the b. So what is the period length on this one?
6 pi.
6 pi.
Whoa, whoa, whoa.
Whoa, whoa.
Where did
Yes.
that come from?
Okay, okay. So it's 2 pi over b. That guy.
Ah,
Okay?
okay.
2 pi over 1/3 gives us 6 pi. So that means my sine, instead of going from 0 to 2 pi, it's going to go from wherever my endpoints are, from 0 to 6 pi. It's a lot stretched. Yeah, it's you'll do a keep change flip. 2 pi times 3. Breathe. It's okay. It's okay. Safe space. It's okay to ask questions. Totally fine. It's a safe space. I like to say it's like Planet Fitness in here. Judgment free. I was going to say, yeah, do I need to get a lunk alarm in here if we start judging people for questions? I'll get a flashing light somewhere. All right. So our left endpoint, we figure that out by figuring out where, that's not what I meant, not that one line. I'm trying to zoom. There we go. Where this thing equals 0. So our left endpoint, that's when we do our 1/3 x minus pi. I want to know when that equals 0, because that's normally where we start.
3 pi.
Mm-hmm. Solve this around. We're going to get our left endpoint is at 3 pi. Add pi to both sides and multiply by 3. Our right endpoint, we do the similar thing, our 1/3 x minus pi. Normally, sine ends at 2 pi, so I want to know when this thing gets around back to 2 pi.
1 pi. No, 3 pi.
Say, add pi. We have 1/3 x equals 3 pi.
Actually, 9 pi.
9 pi. Other way to think about it, if you find your left endpoint, add your period, same thing. Okay? That's another way to do it, is you can take your left endpoint, add the period length. Doing both lets us kind of double check everything and gives us kind of a built-in spot check. So I need to make sure we can get 3 pi and 9 pi on my graph. That's how I decide what I'm numbering by. I need to get from here to here, and we need to make sure we include at least 2 full periods. So I'm going to count by ones. 1 pi. Just because I need to get all the way up to 9 on these axes. So we're going to go with pi and 2 pi. And then I'm going to skip because I don't want to number every single one. There's 4, 6 pi, 8 pi, 10 pi, minus 2 pi, minus 4 pi, minus 6 pi, minus 8 pi. No, it's still new. It's okay. It's okay to make mistakes. Do not demand perfection of yourself. Demanding perfection of yourself sets you up for only disappointment. Do you know how many times I have not handed out the right papers to that table in particular? I mean, come on. It is a daily basis. I don't know why. That column center table never gets the right number of papers. Ever.
Like him before.
Yes. I've also had it where it's been 2 for 4 people. I don't know why. But we are humans. We are not robots. Do not demand perfection of yourself. It shan't happen. Okay. So this lets us get our sine started. We know where our left endpoint is. We're going to start at 3 pi. So my left endpoint's gonna be right here. My right endpoint is over at 9. What do we do from here? Yeah, halfway between we're gonna have another 0, right? Because remember, it's gonna go up, back to 0, and then down, back to 0. So halfway between 3 and 9, which is right on 6, we're gonna have another 0.
So is the middle one gonna be between 4 and 5?
Yes. Yes. So our top piece is going to be halfway between the two. It winds up being at 4.5 or 9 pi over 2. So it's like a thing, but since our scale is so off, it's actually winding up at a halfway, which is unpleasant, but it's there. And it needs to be up at 2 because that's my amplitude. So halfway between on this one, we're going to go down 2 because that's my amplitude. So it winds up being in between, and that's okay. We can do that. It's not super pleasant, but it's fine. So this is our first
Can I ask how much right here?
sine cycle, because our left endpoint was at 3 pi.
How do you know one's not up? How do you know one's up and not down?
Because our amplitude is positive,
Yeah.
and so if I take sine normally goes up to 1 as we go around our unit circle this way. So it goes up to 1, positive 1, and then back to 0, and then down to negative 1. So it's going to start going up unless our amplitude changes that for us. So if we had like a negative amplitude, it'd be the only time it changes.
Oh.
Okay? So that's our sine pattern. We can continue that on where we have points and my zeros are happening every like 3 dashes here. 1, 2, 3, 1, 2, 3, like this. So we're gonna go down to 2 and back, up to 2 and back, down to 2 and back, up to 2 and back. So it's gonna look kind of like this. So our asymptotes for our cosecant are gonna happen everywhere our sine is 0. So our asymptotes are going to happen. Our very first one on sine is right at our left endpoint. I'm going to have one here and here. And then we have another one here. We have another one here. And another one here. And another one here. We have a bunch. Where are our asymptotes happening? I was like, our first one was at 3 pi. Our next one was at 6 pi.
3 pi.
Gorgeousness! I love that. Because we had our 9 pi and we are also at 0. So we are at 3 pi times any other number, any integer. When we're writing these like that with a 3 pi n is always assumed to be an integer. So a counting number. So when we're looking for our cosecant, we're going to take those peaks where we have our top and our bottom on sine. And that's where we start for our cosecant. So this is my first dot for cosecant. And then we approach our asymptotes. I don't even need to think the in-betweens anymore. We're just going to go close to the wall, and go up, close to the wall, and go up. On our low points, we're going to go down, approach our asymptotes. And that's my first cycle on cosecant. So it's all based off of sine. Yes, dear?
Is it always gonna be that pattern where like the uphills are gonna go up?
Yes. Your cosecant and your sine should never like cross. They're only ever going to hit at that one point. So it really only adds like 2 steps to our sine to do our cosecant. And also don't cross your asymptotes, even though I'm bad at drawing. And will sometimes accidentally draw it like that, and not meaning to. That was a straight line. That is not what we're going for. I am also not an art critic and shan't judge your drawing skills, because I am clearly so good at drawing pictures. I am the best at it. My children know definitely to come to me if they have math questions, and go to my husband if they have any questions about drawing things. Because my husband has a fine art degree. I'm married an artist. I can't draw nothing. When we get to things like story problems, all my pictures are so pretty. They're fantastic.
When we're doing story problems?
We will do story problems.
When?
We will. All right, let's do our domain and range on this one. What is our domain? Yeah, it's everything except our asymptotes, right? I heard it. It was just in the midst of conversations. So it's all real numbers except x cannot be any of our asymptotes, that 3 pi over n, or 3 pi n, not over n. All real numbers except the asymptotes. What is our range? Gorgeousness. Fantastic. 2 to infinity. Okay. Cool. I was like, they look scary. They're kind of intense. Say that again. Because that's where the purple is. We're only caring about the purple. The gray is just the tool we use to get there. So we're just looking at the purple. It goes from negative infinity all the way down here, up to here, and it stops. So it goes from negative infinity up to the -2, and it stops. And then it jumps, it teleports. Our next lowest point is at +2, and then it goes up forever. I'm just gonna put that sign back in there, just because I like to have it. Boop, boop, there we go. One more. Okay. Last one for today. Because we also have 10 minutes. So, again, basing this off of sine. So we're going to start by looking at sine with all these same transformations on it. So we're going to look at sine of 2x minus pi over 4 plus 2. What do we notice on here?
The line, the K.
The k. The center of our sine is going to shift. Which way?
Up 2.
Up 2. So the center of our sine is going to be based here. What's our period length going to be for this one? Yes, because we take our 2 pi and we divide it by our b. So the period length is going to be pi. Let's get our endpoints. We want to know when this whole statement equals 0. So we're going to take our 2x minus pi over 4. We want to know when that equals 0. Not quite. Not pi over 2. Because we'll have our 2x equals pi over 4. What do we need to do? Pi over 8. So our left end point's at pi over 8. I said 8. Sorry, it's my handwriting's as I have to zoom in super far on this thing anyway. So do the same thing for our right endpoint, our 2x minus pi over 4. We want to know when that gets all the way around to our 2 pi. It's going to be 9 pi over 8. So since we know we're going to need to wind up at pi over 8s, and our period is shorter, so I don't need to count by pi over 4s. I would rather not wind up in between gaps for like my zeros and stuff. So I'm actually going to count by pi over 8s. We can count our x-axis by whatever we want. And since we're starting at over 8s, I'd really like those to be on actual points. You don't have to, but like it makes it easier. So I'm going to count this by pi over 8, which makes this one pi over 4, which will make skip this one be pi over 2. Then we're at skip 3 pi over 4. What's up? So we add pi over 4. It's going to make our 9 pi over, 9 pi over 4. I'll do it because doing it in my head is not working, and then we'll do it later. 2x minus pi over 4 equals 2 pi. So we add our pi over 4, we're going to have our 2x equals 8 pi over 4 plus pi over 4 gives us 9 pi over 4. When I divide by 2, I'm going to change my denominator so that x is 9 pi over 8. Okay? Yep. Because I know if I put it here, it's going to be like super tiny. All right. So counting like this. Ooh, screen's going to flip. There we go. So that makes this guy pi here, which makes the one right next to it my 9 pi over 8. So what's our amplitude on this one? 1. We don't have a number out in front. So we're going to start at our pi over 8. We're going to end at our pi over 8. Halfway between, we're going to have another 0. We're going to go up 1, then back down, down 1, and back up. So our sine curve is going to look kind of like this. Because our amplitude is only 1, so we go up 1 from our center line and down 1 from our center line. Our asymptotes occur where we hit that center line because the shift happens after the 0. So this counts as our 0. So our asymptotes are in these spaces here. It's where our endpoints are going to be for sine. So our asymptotes for cosecant on this one, we're going to have one here. And this one, which is 5 pi over 8. This one, which is 9 pi over 8. This one, which is minus 3 pi over 8. This one, which is minus 7 pi over 8. When we're looking to figure out what interval is happening here, we're going to pick our first asymptote that we found. I'm going to take my pi over 8. How much did it move to get here? We added what to get to this next one? This was this is 5 pi. It's like 5 pi over 8. Yeah. So we added pi over 2. And on this next one, we add pi over 2 to get to the next one. And then we add pi over 2 to get to the next one. We add subtract pi over 2 to get here, subtract pi over 2 to get here. So it's the pi over 2, this space between, times whatever number we want. That's how we figure out this interval, and that's probably the weirdest part on these. So we pick our first one, We figure out the distance between them, which on secant and cosecant is going to be half of the period length. Yes, dear.
Mr. Okay if we could like do like the same denominator as a
Yeah,
over 8?
totally fine, totally fine. If you want to put it as 4 pi over 8, totally fine.
Thank you.
Yeah. So this is where we get our asymptotes, is that kind of equation. So you pick one to start with and we figure out how it's changing between them. It's unpleasant and it looks gross, but that's what it is. From here, we can grab everything else we need. We're gonna start at our bottom pieces. I'm gonna grab the chunkier pen because I don't like how skinny that is. And we're gonna approach our asymptotes. We're gonna take our upper pieces and approach our asymptotes. They're gonna look like this. That one does not approach the asymptote very well, but it gets the job across. Okay. Gonna grab this. That's from there. Okay, so the domain honestly will not fit on the space here. Our range, we can see that. Our domain is all real numbers except for this thing. X can't equal that, and that's just how we write it. Okay. So it's very, 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 very much based off of our sines and cosines. Secant is the same vibe, based off of our sines and cosines. Okay? So, 6-5 was all about sines and cosines, right? So since we're not in sines and cosines, I have here homework 6-6. Which is not due this week. Because it has secant in it today, cosecant, which we're going to do tomorrow, and tangent and cotangent, which we're going to do next week. Okay? So this has all of those in the next 8 graphs. So if you just need to focus on the sine and cosine right now, I get that. I'm going to put it out there. It's next to the algebra homework. Don't pick up the algebra stuff. Polynomials. You don't want that. You want the packet. That's your homework. Okay? That one will not be due until next week, at the earliest Tuesday. At the earliest, because we won't get tangent cotangent until Monday at the very earliest. Okay? It is about to ding on us. There it is. Have a great rest of your day. Happy Thursday. Bye.